Welcome back to the Deep Dive. Today, we have something really special. We're going to be pulling exclusively from a single, very dense document. It's the Daily Mentorship Digest from Tuesday, December 9, 2025.
And this one comes from the services of KING-KAMBUF PS architecture. It's a remarkable document, not because it's, showing off flashy new building shapes or some new aesthetic.
Right.
It's remarkable because it lays out this mandate, this really explicit mandate for what it calls the globally fluent designer, builder, governor.
Okay, that job title alone, designer, builder, governor, we have to unpack that immediately. I mean, we're so used to thinking about design in, what, 3 dimensions?
Right, space, X, Y, and Z.
Exactly. And this digest, it just throws you into this 4-dimensional world of systems, of consequence, of time, and maybe most importantly, accountability.
It really does. It forces you to think about how architecture behaves over decades, not just on opening day, but across multiple political cycles, huge technological shifts, and, well, all this escalating environmental uncertainty we're facing.
So our mission today, for you listening, is to really try and provide the intellectual toolkit you need to operate at this level, at this system scale.
Precisely. This entire deep dive is about designing for things that, honestly, architects have traditionally tried to keep off their plate. Things that don't show up on the drawings.
Like what?
Like professional liability that stretches out for a decade. Or the deep influence of insurance and actuarial models on the actual structure of a building. The friction of bureaucracy. And this really interesting one, the hard metrics of speed, or as the source calls it, latency.
So this isn't about drafting a blueprint anymore. It's about designing a complex, almost a living policy instrument that functions over a long duration.
That's the perfect way to put it.
So by the end of this, you should have a kind of shortcut to understanding this systems scale perspective, the mindset you need to shape not just buildings, but time, governance, and consequence itself. Let's start with a concept that feels like it just changes the game for high-performance facilities.
Okay, so the first big conceptual shift that the digest signals is the rise of what it calls latency-aware architecture.
Latency-aware?
Yeah, and for, the last few decades, the way we measured a digital facility, or really any network building, was all about bandwidth. How much data can you push through the pipes?
More is better. A bigger pipe is a better pipe.
Always. But the digest argues that's yesterday's metric. The new metric is delay. It's about designing for minimum decision time lag.
So it's not about how fast the data travels, but how quickly that data can be turned into an action, an actual real-world response.
Exactly. And this is where it gets so critical for us, for architecture, because this isn't just for, high-frequency trading floors anymore, even though they're kind of the classic example.
Right.
This now applies to all kinds of advanced civic facilities. Think emergency response hubs, military command and control centers, autonomous transit control for a whole city, even specialized medical facilities. The physical building itself is now a measurable, critical variable in that speed equation.
Wait, hang on. So you're saying that the actual physical distance that data has to travel through a fiber optic cable, or even the distance a key person has to walk from one room to another, that is now a primary design metric.
A primary design metric.
Potentially overriding things like aesthetics, or even what we would consider traditional spatial programming.
It has to. The source material is really clear on this. It says floor plates, vertical cores, the physical adjacency between a server rack and the human operator, all of it must be physically shaped to minimize lag.
Wow.
It's this acknowledgement that, well, both the speed of light and the speed of human thought are constrained by the physical reality that we build.
Okay, let's break that down with a practical example.
Yeah?
In a data center, right, milliseconds are everything.
Everything.
So if I, as the architect, place a server rack 50 feet further from the main network switch that it absolutely needs to be, that tiny bit of distance introduces a delay.
A delay that could literally translate into millions of dollars lost in a financial setting. Or, and this is the key point for civic architecture, in a crisis setting, it could be lives lost. Architecture is now influencing reaction time.
That's a heavy responsibility.
It is. And if you connect that to the bigger picture of public service, it means architecture is now directly influencing the speed and, frankly, the effectiveness of governance and emergency response.
There's a question in the digest about this, right? One of those ARE-style questions.
Yeah. Question 7. It's a great one. It asks, why must public agencies evaluate decision latency caused by building layout?
It's such a direct challenge to conventional planning.
And the answer is just so stark. It's because spatial separation, physical distance, inherently slows down a government's response. It just does.
So if you have the police chief on the 3rd floor, the mayor's crisis team on the 5th, and the infrastructure director down in the basement.
You've just created bottlenecks. That physical separation introduces friction, it introduces delay, so the architecture itself becomes this key managerial instrument. It either speeds up critical decisions or it slows them down.
It makes the design of a corridor or an elevator suddenly less about just simple egress and more about kinetic efficiency.
Exactly.
If your building's layout is inefficient, the organization inside it will be inefficient, especially when it's under stress. We see this with another question, Q1, which defines spatial latency.
And the principle is so simple. Physical distance between key program elements directly affects decision speed. Full stop.
The lesson here feels paramount then. Circulation, adjacency, where you put the communication hubs, these aren't secondary things you figure out later.
They're operational bottlenecks, and they must be managed architecturally. You are literally designing the velocity of the organization that will inhabit your building.
And the digest really drives this home with a design drill, a scenario.
Yeah, it's a great one.
Design a facility. It gives examples like a crisis tribunal, a command center, or an emergency ops facility, where decision time, measured in seconds, is the #1 design metric.
This exercise just forces you to abandon all your traditional comfort zones as a designer. You have to embrace constraints driven purely by function and speed. And the constraints they list are, well, they're intense.
Let's go through them. Constraint #1. No corridor may exist without explicit operational justification.
I mean, just think about that. That's brutal. It just strips away every single aesthetic hallway, every buffer zone, every space you might have designed just to, elegantly separate two departments.
Hold on.
It demands total ruthless efficiency. You have to be able to point to every single foot of circulation in your plan and say, this distance facilitates the transfer of X information from person Y to system Z within 1.5 seconds.
And if you can't justify it, it's out. It's just latency waste.
It's waste.
But here's the pushback. Doesn't that create a building that feels incredibly cramped? Or even chaotic? You're jamming everything together for raw efficiency. How does that affect human performance? How do you maintain the clarity and the calm you need for high-stakes decisions in that kind of environment?
That tension is the whole point of the drill. It's the central architectural problem to solve. And before we get to the chaos part, look at constraint #2.
Right. Vertical circulation must be designed to outperform horizontal circulation speed.
So in a multi-story EOC, this is a direct attack on conventional elevator design. You can't just have a bank of standard elevators.
No, you'd need dedicated lifts. Or some kind of rapid vertical transport system, something that can get a core decision maker from, say, the secure comms center on the 4th floor to the press briefing room on the ground floor, faster than they could walk across even a minimized floor plate.
And that influences everything. It changes your core placement, the technology you specify, maybe it's dedicated high-speed shuttle elevators, and even the structural rigidity you need for faster acceleration and deceleration. It's a cascade of design decisions.
Which leads right back to my question about chaos. Because the final constraint is the most architecturally fascinating one.
It is.
The final architecture must visibly express urgency without devolving into chaos.
How do you do that?
That's the question. How do you design urgency? Is it just raw concrete and exposed systems? Or is there something more subtle at play?
I think it has to be more subtle. It requires a really careful study of the psychology of operational efficiency. It's about materiality, it's about sightlines, it's about lighting. All of it has to communicate serious, immediate function, but not panic, not frantic movement.
So you might use materials that minimize glare and distraction. You might use strategic directional lighting to guide people and focus attention.
And sightlines that instantly show you the status of adjacent teams without you having to leave your station. But the structure itself, the shell, it has to feel anchored. It has to feel reliable, even if the functions inside are moving at maximum velocity.
The entire exercise just shifts the architect's focus. You're not designing a beautiful vessel anymore. You're designing a systems accelerator. And the success of your design is measured in milliseconds saved. Okay, so let's shift gears. We're moving from the speed of data to the speed of carbon. Part 2 of the digest introduces signal B, and this is another profound systems scale shift. Construction sequencing as a climate strategy.
Yeah, this is a big one. For the last, 20 years, we've been obsessed with total embodied carbon. The big number, the cumulative sum of all the emissions it takes to create a building.
Right, the final tally.
But this signal introduces a temporal dimension, a when. It points out that high-performance projects, especially the ones with public or climate-conditioned funding in Europe and parts of Asia, are now adjusting their construction schedules to specifically reduce carbon spikes.
So it's not just how much carbon, but when you release it, the timing actually affects the emissions intensity.
Exactly. And why does that matter? Because a massive concentrated emissions peak, say, from pouring all your concrete in a single month, can overload a regional energy grid or just align terribly with global carbon accounting periods. It has real-world effects.
This fundamentally changes construction management then. It's not just about the classic triangle of time, cost, and quality anymore.
It's not. It's now a climate performance discipline, and it has real ethical and legal implications.
So let's define the constraint here to make it real for everyone. Imagine a large public project has to meet a carbon intensity cap per month.
Right, a monthly budget. Maybe the city's funding is tied to it, and they only allocate a certain carbon budget during the summer months when the grid is already strained.
In that case, the conventional approach of just optimizing for speed, it's totally out the window.
Completely. The contractor can't just rush through all the concrete pours, which are usually the highest emissions activities, just to get the structure up as fast as humanly possible. They have to engage in what the source calls temporal optimization.
Which means the architect, as this designer-builder-governor, has to build this climate metric into the design phase from day one.
You have to. You can't just hand it off to the contractor and say, good luck. The source details a professional task focused on this, and it lays out a really disciplined workflow. It's 5 steps that a system-scale practitioner has to master.
Okay, let's walk through them. Step 1.
Step 1 is the foundational analysis. You have to identify which phases of construction contain the high-carbon activities, and this requires a really detailed life cycle analysis. You're differentiating between the emissions from concrete production and curing, from steel fabrication, from transporting specialized equipment, from installing the mechanical systems. You need a very fine-grained carbon profile of your entire project schedule.
Step 2 is the temporal optimization itself. This is the big move. You sequence the work specifically to flatten those emissions peaks.
And this is where the cost-benefit analysis gets really, really complicated. For instance, you might decide to spread out those massive concrete pours over, say, 8 weeks instead of just 3.
But that has huge knock-on effects. That might mean you need double the formwork on site, or you have to extend the lease on the crane for another month. That introduces schedule delay and direct cost increases.
Right. And the architect now has to quantify that. You have to be able to say, okay, the monetary cost of this delay is X, but the climate benefit of this temporal optimization is Y.
You might save 5 tons of peak carbon, but it costs an extra $50,000 in rental fees.
Exactly. And then you have to defend that decision to the client, to the public. You have to prove that the ethical and legal necessity of meeting that monthly climate cap outweighs the immediate financial hit.
That's a new skill set.
Yeah.
Okay, step 3.
Step 3 requires resource management fluency. You have to adjust crew size versus equipment intensity to manage the output. For example, a huge concrete pump machine might be a massive carbon contributor because of its fuel consumption or its own manufacturing embodied carbon.
So you might decide to use a smaller, less energy-intensive machine, but with more skilled labor over a longer period, just to keep your monthly emissions intensity under the cap.
It's a constant trade-off. And that leads to step 4, which demands supply chain fluency. This pushes the architect way beyond the traditional site boundary.
What does that mean?
It means you have to coordinate your construction schedule with your supplier's specific production cycles. For instance, if your local steel fabricator tells you that their plant runs on peak fossil fuel-intensive electricity during the day,
Then you might schedule your high-volume orders for delivery during their night shifts, when renewable energy sources might dominate the grid mix.
Exactly. Which means the architect has to basically understand the energy sourcing of their suppliers. That is a massive expansion of professional responsibility.
It's huge. You're moving from just designing a building to managing external logistics and even engaging with energy policy.
And that brings us to the final step, step 5, which is all about accountability. You have to document all of these trade-offs for public accountability. Because the sequence you've chosen is based on climate ethics over pure speed. These complex decisions, the delays, the cost increases, they have to be thoroughly traceable and defendable.
The ultimate lesson here is just so stark. The order of construction, the specific timeline of what you do when, now carries this incredible ethical, legal, and measurable climate weight.
We are absolutely moving away from that famous project management triangle of fast, good, cheap.
Right.
We're in a complex four-dimensional matrix now. It's fast, good, cheap, and temporally carbon optimized, and you can't always have all four. And this commitment to long horizon thinking, it completely dictates a fundamental shift in professional accountability. It has to.
Which brings us to Signal C in the digest, and this one.
Yeah.
It feels like it's going to make a lot of practitioners very nervous.
It should. The mandate is that governments are starting to require 5 to 10 years of post-occupancy data reporting for civic and publicly funded projects.
5 to 10 years, that is a profound extension of professional liability. It's not just, does it meet code on day one?
Not anymore. This means the architect isn't just handing over a static object anymore. You are effectively warranting its operational performance, its energy efficiency, its functional utility for up to a decade.
And all that data, everything from HVAC efficiency to how people are actually moving through the building, that's going to be collected?
Collected and used, it will explicitly inform future government contracts and project proposals. If your building performs poorly 5 or 7 years down the line, that hard, quantifiable data comes back to haunt you. It impacts your firm's reputation and your ability to get future work.
The risk profile for just practicing architecture has been dramatically extended.
Absolutely. If the building systems don't adapt to changing internal loads over time, or if the energy performance degrades way faster than projected, the architect is now directly on the hook.
Which means you have to design for loads and variables that are completely external to the structure itself. And the ARE questions in the source highlight this beautifully.
Let's start with the political reality of it all. Our question 2 asks why long-duration civic projects must specifically consider political cycle load changes.
Political cycle load changes. We're talking about analyzing a political structure as if it's an actual quantifiable design load, like snow or wind.
That's exactly it. It's a concept that is almost entirely absent from traditional engineering education. But a change in a mayor's office or a new administration, that's the variable load of governance, and it can completely alter a building's functional demands overnight.
How so? Give me an example.
Well, a building designed today for maximum public transparency and openness might, under a new, more security-conscious administration, suddenly need heavily fortified security retrofits, rapidly implemented.
So you need to change entry sequences. You might need to reinforce walls that were never meant to be load-bearing in that way.
Exactly. And the structure and its systems have to anticipate this political variability. You have to design in the flexibility for these massive spatial pivots. Maybe it's a sudden expansion of staff in one department, or the need to convert what was an open office space into a highly secure, segmented briefing room after some new geopolitical event.
You're designing for future political unknowns.
You are. And then there's the issue of just things getting old. Q3 covers this, focusing on hospitals and what it calls phased system obsolescence.
Right.
The core structural lesson here is that the mechanical, electrical, and plumbing systems, the MEP, their life cycles almost never align with the structural lifespan of the building.
Especially in a hospital. Medical technology updates every few years, but the concrete structure might be good for a century.
So you can't design a static hospital. You have to design a shell, a framework that is built to facilitate perpetual replacement, modification, and technological upheaval, all without shutting down critical operations.
What does that look like in practice?
It mandates very specific structural considerations. You're designing oversized vertical access path. You're creating dedicated utility shafts that can accommodate completely new systems without having to do invasive demolition. You're thinking in terms of modular infrastructure zones.
So the structure needs to be porous. It needs to be accessible enough to allow a major systems replacement cycle every 7 to 10 years, even though the main structural frame stays untouched for decades.
Precisely. And this degradation isn't always from just replacing old systems. Sometimes it's the cumulative stress of constant modification. Q4 addresses this. Tenant retrofit fatigue in, say, multi-tenant research buildings.
Tenant retrofit fatigue. I like that term.
It's very descriptive. Frequent modifications, drilling new holes for new equipment, moving internal walls around, updating services. All of that weakens the anchors. It weakens the slabs over time.
The lesson being that repetition causes cumulative degradation.
Yes. If a pharmaceutical lab or a university research wing gets a major retrofit every 18 months for 20 or 30 years, the cumulative damage to that slab's integrity, all the weakened anchors, the patched up penetrations, it becomes a significant structural issue.
So the structure has to be designed to withstand that fatigue from the beginning.
Mhm.
You might need intentionally thicker slabs or specialized embedded anchoring systems, or you create these pre-designated retrofit zones that isolate all that stress away from the main structural frame.
It's proactive design for churn. And finally, let's look at the infrastructure of density itself. Q5 highlights the evolution of service capacity, specifically that tall buildings must evaluate elevator service degradation over decades.
This one is fascinating.
Vertical transportation systems evolve directly with the density of the city around them. As a city densifies around a tower, the building's perceived capacity and its actual functional lifespan is often governed not by the strength of the steel, but by the wait times and power demands of its elevators.
So increased usage over decades alters the loads, it alters the power requirements. You might need a total mechanical overhaul of your vertical transit system long before the structure itself shows any signs of wear.
It's profound, isn't it? If you design a tower for a certain peak occupancy in 2025, but the surrounding district's density doubles by 2045 because of new transit hubs or other towers going up.
Your vertical infrastructure becomes the immediate, crippling bottleneck for the entire building.
And that means the architect has to anticipate the changing city, the demographic and density load around the building, not just the building's own internal load. It's a whole other level of context. And that brings us to maybe the most powerful, but often the most invisible influences that are shaping global design today, and that's the forces of financial risk and bureaucratic friction.
The digest identifies the first one as insurance-driven architecture.
Yeah, and this is a critical paradigm shift for anyone practicing. We're talking about global insurers who are backed by massive reinsurers with incredibly sophisticated climate and hazard modeling, and they are increasingly dictating specific design constraints.
Things like material exclusions, or what kind of facade system you can use, or mandatory flood elevations.
And they are dictating these things before the local building department, the AHJ, even gets a look at the drawings.
So the core insight here is that architecture is being quietly shaped by actuarial models, not just by zoning codes or the building code.
That's it. Insurance underwriters, armed with this incredibly detailed global climate risk data, are becoming a kind of de facto non-governmental design review board. And they have veto power.
If an insurer refuses to cover a certain type of exterior insulation finishing system because of poor fire performance data from somewhere else in the world,
Your client can't get insurance, so you can't use it.
or if they require a flood elevation 5 feet higher than the regulatory FEMA minimum because their own sea level rise projections are more aggressive,
Then their risk policy effectively overrides both your architectural preference and the standard code. You build to their level, or the project doesn't get financed.
you see this explicitly in Q3's focus on material exclusion coordination. The architect now has to coordinate directly with the client's insurance broker.
Because some of these major insurers will simply refuse to offer liability coverage for specific systems. Full stop. Risk policy can, and very often does, override architectural intent.
So the architect is now operating with this dual mandate. You have to satisfy the building code, and you have to satisfy the global risk matrix of the reinsurers. And if you fail the second one, the project is either uninsurable or it's burdened with such high premiums that it's just not viable.
And the digest really drives this point home with this incredibly stressful but completely realistic scenario it calls the mid-design crisis.
Okay, let's set the scene.
You have a high-visibility, flood-adjacent civic or commercial project. You are at 65% design development, so late stage. A huge amount of money has already been invested.
And you get the call.
You get the call. The insurer has just withdrawn coverage because their updated climate models show a significantly increased risk. Your budget contingency is limited, and the political visibility on this project is high.
That is a professional crisis, a conventional firm. I mean, that could be a project-ending event.
For a lot of firms, it would be. But the systems scale practitioner has to treat this as a structured risk management problem. The source details a 4-step professional workflow you have to go through to salvage the project.
All right, let's walk through it. You get the call. Step 1.
Step 1. You have to immediately map the insurer's objections to specific design features. You have to translate their abstract actuarial rejection, which might be something like unacceptable catastrophic loss potential due to revised flood probability, into precise architectural terms.
So you have to figure out, okay, this means we have to raise the lowest finished floor by 24 inches, or we have to eliminate all non-structural openings below this new datum line.
Exactly. You make it concrete. Then step 2. You identify structural or planning alternatives that have an explicit actuarial impact. Your solutions can't just be fixes. They have to be changes that you know will demonstrably lower the insurance premium.
So you're modeling solutions. Maybe you raise the entire ground floor. Maybe you implement a sacrificial perimeter wall system that's designed to fail gracefully in a flood.
Right.
Or you change the whole material palette of the first two levels to hardened, moisture-resistant components.
And every single one of those alternatives has to be quantified based on its risk reduction impact. Which leads to step 3. You develop comparative premium scenarios.
This is the financial core of the crisis, right?
It is. The owner needs a detailed comparison. What's the difference between staying the course and risking no coverage or cripplingly high premiums versus the cost of the redesign, factored against the future premium savings over the next 10 years?
So you're justifying a $5 million redesign today with a projected $15 million reduction in operational risk costs over the long term.
That's the language you have to speak. And that's step 4. You present the owner with a detailed risk-cost-time matrix. Every redesign option is weighed against its financial impact, its schedule extension, and its quantified reduction in long-term risk exposure. You're not talking about aesthetics anymore. This is executive decision-making. Risk management is now just part of the core design process.
Wow. Okay, so moving from the financial constraint of risk to the temporal constraint of bureaucracy. Talking point 3. Permitting delays as a primary design constraint.
This is a reality that is just maddening for every firm in a major city. The permitting timelines frequently exceed the actual construction durations now.
Which is incredibly frustrating. But for the system scale practitioner, the source argues this is actually an opportunity.
It is. The professional skill of an architect who understands these complex bureaucratic workflows, who can create proactive permitting strategies, that architect will often outperform one who just focuses on a perfect set of technical drawings.
So the fastest path to groundbreaking isn't through a more efficient site crew, it's through the building department.
Increasingly, yes. And the challenge is to design a permitting optimized project strategy that speeds up approval without gutting your architectural ambition.
So what does a permitting optimized strategy actually look like on the ground?
Well, it can mean a lot of things. It can mean breaking the project up into smaller, more easily approved subphases. For example, you submit the foundation and excavation package long before the full structural and facade package is even finalized. Get that permit first. Get in the ground.
So you're de-risking the schedule.
You're de-risking the schedule. It also means pre-approving complex or specialized systems, like a performance-based fire engineering solution or an unusual curtain wall assembly way before the full package is submitted. You can use third-party peer review to preempt the inevitable questions from the bureaucracy.
So you're essentially designing the submission process itself. You're treating the review workflow as a critical path item that has to be managed and expedited, just like pouring concrete.
That's the perfect analogy. And it requires the architect to become a master of what the source calls regulatory inheritance. You have to understand exactly which documents, which analyses, and which external reviews need to be prioritized to bypass the procedural bottlenecks in your specific jurisdiction.
Let's pivot now to how architecture can address environmental extremity and even societal conflict. We're moving into some really long horizon scenarios here. Talking point 2 in the digest discusses the rise of subsurface urbanism.
And this is going so far beyond just building a few floors of underground parking.
Right, this isn't just a basement.
No, this is strategic urban planning. The digest points to dense cities like Helsinki, Montreal, Singapore. They aren't just building basements, they are dramatically expanding their civic space below grade. We're talking logistics hubs, entire transit systems, utility tunnels, and even emergency housing.
So underground development is now being seen as a critical strategic planning solution. It's a response to density, to climate risk, to resource constraints. It's not a last resort for when you run out of space.
It's a first choice for certain types of infrastructure, but if you're building these structures that are designed to last for a century deep below the ground, you're dealing with structural forces that are constant and cumulative, which is where Q2 comes in.
It raises a specific engineering need, the requirement to assess long-term hydrostatic creep.
Hydrostatic creep. It sounds technical, but it's a critical detail. We're not just talking about the immediate hydrostatic pressure of water pushing on the foundation walls.
Which is what we normally calculate for.
Right. Creep refers to the slow, time-dependent deformation of materials, in this case concrete, when it's subjected to a constant sustained load, like that unrelenting water pressure, over decades and decades.
So why does that matter more than just the initial load calculation?
Because the effects are cumulative. It's like a slow-motion punch. Over 50 or 100 years, this constant water pressure causes microscopic material fatigue. The structure has to be designed using specialized, highly dense concrete mixtures and advanced waterproofing and lining systems to resist this relentless, time-dependent displacement without significant cracking or leakage.
So you are literally anticipating failure over a century, not just resistance to the initial forces on day one.
You have to, and that structural reality feeds directly into the human problem. The design challenge here is profound.
Which is, how do you design a subterranean public building that meets all the psychological, wayfinding, and life safety expectations people have without being able to rely on windows or a view?
Right, without constant artificial openness or reliance on conventional exterior views. This demands a really deep understanding of human factors. You are actively managing the human experience of sensory deprivation.
So what are the solutions?
The solutions are things like utilizing carefully controlled artificial light cycles that actually mimic natural daylight shifts, using materials strategically that suggest natural textures or geological formations, and creating incredibly clear, intuitive wayfinding that doesn't rely on being able to see a landmark out the window. The design has to actively mitigate claustrophobia and disorientation.
Okay, now let's combine all of this, risk, governance, environment, into what might be the most ambitious conceptual project drill in the entire digest.
The Climate Risk Judicial and Arbitration Complex.
Yeah, this is a facility built specifically for resolving incredibly high-stakes disputes. Things like relocation claims after a climate disaster, insurance arbitration after major infrastructure failure, and climate liability cases between corporations and governments.
And the brief positions the building itself as a neutralizing device. The architecture is designed to actively reduce confrontation and increase clarity during these high-tension, high-stakes proceedings. It's an explicit architectural intervention into the legal and governance process.
The spatial adjacency goal is fascinating. It says the design must deliberately slow emotional escalation without impeding procedural efficiency.
I mean, how do you use architecture to calm people down?
That's the question. Does it mean using soft lighting and muted acoustics? Does it mean creating long, deliberately paced circulation paths that you have to walk down before you even enter the high-conflict space?
Absolutely. It's all of those things. The design uses spatial pacing, acoustic dampening, and material texture to literally try and manage people's stress hormones. And the constraints detailed in the digest define this neutrality perfectly.
Okay, what are they?
First, no monumental gestures. This removes architectural ego, it removes spectacle, it removes the traditional display of governmental power. The focus has to be entirely on the resolution process, not the imposing nature of the building.
Second constraint, equalized spatial hierarchy between all parties. So the opposing sides, the mediators, the observers.
Everyone. It's a spatial expression of justice and fairness. You have to ensure that no party feels architecturally disadvantaged or intimidated or placed in a subservient position by the setting itself. And that's vital when you're talking about complex arbitration claims.
And the third constraint.
The structure must express permanence and neutrality, and that translates into using monolithic, reliable materials. It means controlled views. Maybe views focused inward on a contained natural element like a courtyard, rather than out at the busy city. It's about creating a sense of gravity that anchors the whole process and promotes rational thought over an emotional reaction.
Finally, we have to look at the persistent threat landscape, which comes up in Q4. Why must civic buildings analyze security retrofitting paths? This ties right back to that political cycle load we talked about earlier.
It does, because threats are dynamic. Terrorism, civil unrest, specific targeted attacks, the security needs of a public building change constantly. The ultimate lesson here is designing buildings that can, as the source puts it, tolerate paranoia.
Tolerate paranoia.
Meaning they can be adapted quickly and economically to new security needs without fundamental structural alteration. This involves pre-planning for new vehicle checkpoints or thickened entry points or the future installation of bollards or hardening specific interior zones. The security plan for the building has to be evolutionary, not static.
Okay, for our final segment, let's bring it all back to the nuances of resilience and the deep understanding required for structural loads and regulatory compliance. Q7 in the digest makes a really crucial distinction about what resilience even means.
It does, and it's important because resilience is often mistakenly defined as just avoiding total failure. A building is resilient if it's still standing after the hurricane.
Right, pass-fail.
But the digest argues that real resilience is actually about operability under compromise. Partial failure is the more common, the more critical, and frankly, the more insidious problem.
So this requires designing for what it calls graceful system failure.
Graceful system failure. It's a great term. If a major event happens, let's say one of your two main power substations fails, the building doesn't just go dark.
No, it shifts.
It shifts instantly to a prioritized secondary system that maintains only the essential functions. Communications, critical medical systems, essential ventilation, key vertical transit. Even if the non-critical amenities like decorative lighting or certain HVAC zones have to shut down.
And Q1 reinforces this, focusing on post-event functional downtime in flood resilience.
Yeah, and the point is so important. Structural survival does not equal operational usability. If your hospital building survives a major flood structurally intact, but it takes 9 months to dry out and replace all the damaged internal systems on the ground floor.
Then it's functionally useless. That's not resilience.
Not for a critical civic facility, no. The design focus has to shift to recovery time, not just resistance. And that means prioritizing dry systems, placing all your critical equipment well above any projected flood levels, and using easily replaceable moisture-resistant components for the lowest floor plates. You are designing for a rapid system restart.
The sources also point out that we often overlook loads that don't fit into our traditional models of gravity, wind, and seismic. Q5, for example, is just so practical.
It's a great one. Long-span roofs must analyze scaffold staging loads.
A load that's caused by maintenance, not by occupancy or weather.
Exactly. The temporary access systems you need for maintenance and construction, the massive, heavy scaffolding and material staging areas that you have to use every few years to repair or repaint a complex roof, often govern the structural design loads more than the actual dead load of the roof itself.
So if you design this huge, lightweight, spectacular roof, but the crews need to erect 50 tons of temporary structure just to service it.
Your structure has to be sized for that temporary construction load, a load that will only exist for maybe 1% of the building's entire life. But it's a controlling load.
That level of detail requires some really deep technical knowledge. And that leads us to the NFPA bite in the digest, the mastery of performance-based code engineering.
Right. This allows modeled outcomes to substitute for the prescriptive checklist-style rules in the codebook.
This feels like the skill differentiator for truly advanced practitioners.
It is. Performance-based fire engineering allows for much more innovative and efficient designs, but it comes with a huge burden of proof. It requires extensive documentation, rigorous computer modeling, and compulsory peer review by another expert.
And the stakes are incredibly high here. The risk is that poor modeling equals severe legal exposure. You are essentially arguing for the functional equivalence of your unique solution, which requires a mastery of complex fire dynamics and egress modeling. It's not just checking boxes.
Not at all. The takeaway is very clear. Advanced practitioners have to be ready to defend the intent of their design under intense scrutiny, not just their simple adherence to a prescriptive rule.
Okay, let's wrap this section up with the complexity of working with legacy structures. Q6 highlights regulatory inheritance.
This is such a critical issue. Adaptive reuse projects are vital for sustainability, but they force you to address these layered codes from across the decades, which invariably creates maddening conflicts and inconsistencies.
The architect becomes a kind of negotiator of history.
That's a great way to put it. The challenge is simplifying this regulatory inheritance. How do you negotiate with the AHJ, the building department, to rationalize conflicting safety standards from 1950, 1980, and the current code all in one building?
It seems impossible.
It's very difficult. It requires a strategy to define the project's performance baseline without triggering every single retroactive code requirement, because that would just make the project economically impossible.
So it requires a political and legal mastery of the codes themselves. You have to understand where negotiation is possible and where you can make a performance-based argument to supersede some outdated prescriptive rule. It's another skill entirely. #outro. We've covered an extraordinary amount of ground today. I mean, we've moved from the need to manage data latency in milliseconds all the way up to the macro-level constraints of climate-driven actuarial models and these decade-long accountability mandates.
This deep dive into the KING-KAMBUF Mentorship Digest really does reveal a profound and I think necessary shift in the focus of architecture. The modern designer, this designer, builder, governor, has to move beyond just form and function.
And learn to actively shape things like speed, ethical climate performance, financial risk profiles, and even governance friction.
Exactly. The knowledge we've talked about today, it reinforces this demand for the designer to evolve into this globally fluent architect, engineer, planner, builder, someone who is truly capable of navigating power, consequence, and risk on a systemic scale and operating with a very, very long horizon.
The sources really leave us with a central tension, though. And I think a really provocative thought for you, the listener, to mull over as we conclude our deep dive today.
And the tension is this. When financial risk and these powerful actuarial models increasingly dominate every single stage of the design process, who truly controls the ultimate form of the built environment? Is the architect? Is it the client?
Or is it the silent, powerful hand of the insurance underwriter?
A question that I think is going to define the next generation of practice.
It really is. Thank you for joining us on this deep dive into system scale architecture. We will see you for the next one.